quickly. Okay. Start the mini recording devices, and we're in business. So today we're going to talk about t-tests. This is stuff that, again, I know you've run into before, but don't feel like you can't ask questions. I'd really rather you did than not. Remember to find the probability of a given, this is what we talked about last time, finding the probability of a value of a variable. If the variable is normally distributed, we turn it into a z-score. That was what we did at the very end, wasn't it, right? Just took something, turned it into a z-score. Okay? So we had, I think it was IQ, just like the sort of standard thing. And z equals x minus mu over sigma. The reason it looks all like that is because I didn't feel like getting out the equation editor software to do one little log. Okay. Look it up in a Z table, you're in business. Pretty easy. Right, stuff you've done before. You learned how to do it last year or whenever you took stats. It's really not a horribly difficult thing to do. It's really quite mechanical almost. Okay. Now, as interesting as this is, and I'm putting interesting in air quotes, we're usually dealing with means, not individual values, right? Like, it's very rare. In fact, I don't ever remember ever worrying about a z-score of an individual, individual z-score. I worry about individual scores or probabilities, let's say that instead, I worry about probabilities of means. I don't worry about probabilities of individual scores. The last time I can think of worrying about the probability of an individual mean, or individual score, was when I found out my IQ. I thought, I wonder what the probability of getting an IQ like that is.
What's your IQ?
I'm not going to tell you. It's a good score. It's not low. Yeah, it's a good score. Starts with a 1. I'll leave it at that.
That's good too.
It's I think you'd like to hope that the person teaching you has an IQ greater than the average. But yeah, I mean, I remember then going, oh gee, I wonder what the z-score for that, the probability of that is this. I guess I'm pretty smart. So, that's literally the last time I did that. Okay, that's a long time ago. Third year. So instead of knowing the distribution of x, we usually care about the distribution of x bar. And I talked a bit about this last time with sampling distributions, right? I talked about how you could, even with rolling a die or flipping a coin, the average of the average is distributed normally. So, because we're dealing with group means, we care about groups. Individual differences, while interesting, and there's a whole part of psychology about individual differences. That's perfectly fine and dandy. But usually we care about groups. This is why, for example, when someone does, for those of you guys who do an honors thesis next year, when someone says to you, how did I do on this? Your standard answer is, I'm not interested in individual scores, I'm interested in groups. That's a way of getting out of telling people anything. It's basically a way of getting out, because what's going to happen is people are going to interpret the score on whatever the thing they did a lot more seriously than they should. Right, so the standard answer you give people when they say, how did I do? You say, well, the first answer you give is, just fine. The second answer is, I really don't want to tell you how you did because I'm only interested in group scores. I'm not interested in individuals. And then they say, yeah, but how did I do? You say, you don't have the expertise to interpret how you did if I give you a score. But you do. No, I don't. You don't give people their individual scores, okay? Because they're not signing up ever to get insight. They're signing up to be in the experiment. Anyway, we're interested in groups. And really the first answer is true. We don't care about individual scores. It's not what we're into. And this tells us about the distribution of means, the sampling distribution of the mean, the central limit there. given a population with mean mu and variance sigma squared, the sampling distribution of the mean will have a mean of mu sub x bar equals mu, and a variance of sigma squared over n. As n increases, this distribution approaches normal, no matter what the shape of the parent population distribution. Okay? Memorize that. No, it's something you should know. It's not hard to memorize a bunch of words. Now, again, we talked a little bit about this last time, but we have a population with a mean of mu and a variance of sigma squared. Fine. We just gave them names. They have a mean and variance. The sampling distribution of the mean, in other words, the average mean score we will get, we take each mean score of size n, of a group size n, and we do it an infinite number of times. Obviously, we can't really do this. And we plot out how likely it is to get a certain mean of, say, size 10, or 15, or 30, or 1,000. The mean's going to be the same. The mean, the average mean, is actually going to be the same size, the same value, sorry, as the mean. That's neat. And not surprising, right? That's intuitively pleasing. The variance is sigma squared over n. Now, and I mentioned this last time, why would the variance be sigma squared over n? Well, we know it's going to depend on n. It's going to depend on it. And as n gets bigger, it's going to get smaller, isn't it? Because think about it. And again, let's just pretend that we got, I don't know, it's 20 odd people here today. We're missing 2 people. But we got 1, what do we have? 1, 2, 3, 4, 5, 6, 7, 20, 21, 22, 23. 23 people here. Okay. And we're going to measure our heights. And if we sampled 5 people, and let's say our average height in the room is 170 centimeters. I don't know what it is. Let's say it's 107. Oh, no, far off. So, we have 23 people as our population. It's not usually like that, but let's say in this case it is. We're going to measure everybody, plot up their average score, average height. Easy, no problem. Okay, we're going to get, we'll do that. We're going to do a sample size of 10. And we're going to do it over and over and over again. We're going to get a nice bell-shaped distribution. That's what this says. We're going to get a mean of 170, the mean, and we're going to get some variance. Now, the interesting thing is, well, think about this. If I only sample 2 people each time, the variance will be pretty big, right? Because there'll be some times when you're going to get, who else in here? Tom's pretty tall. So we're going to get me and Tom as the 2 people, right? And I think probably the 2 tallest people in here. So we're going to get really high. And then some other times it's going to be Jay, and I don't know, Mickey's not very tall either. Okay? It's going to happen too. It's not going to happen that often. But it will happen. And it's going to really spread out. Now what happens on the other hand if we use sample size 23? You say, wait, Dave, you said that was the population. Yeah, this is for illustration purposes only. So we're going to get the same value each time, aren't we? The same value for the height. What's the distribution going to be? It's not a distribution, it's a freaking point. It'll just be this. Done. Okay. Does that have any variance? Well, no, it's the same damn number each time. As n gets bigger, variance gets smaller. Or, I said this the other day, the limit as n approaches infinity of this 0. Now, if it's going to depend on n, so, and if this doesn't make any sense to you, that's fine. But just look at this thing in here, in the parentheses here, sigma squared over n. All that is saying as n gets bigger, because it's a fraction. What's something you do in math that was we make something get bigger, the whole quantity gets smaller? You divide by it, you make a fraction. That's all it is. Okay? The nice thing, as I mentioned as well, is the idea that it's always going to be normal. Always going to be a normal distribution.
Question so far? So memorize that. Also memorize what it means. Not just the words. Words are important, and the words in that order are important. Said exactly like that. There's very few times when I will say that to you, but mathematical things like that actually have to be, they're like that for a reason. Okay? All right. Think of the power of this. It's actually pretty cool. The population distribution shape doesn't matter. That's neat. What matters is random sampling. So those samples have to be random. It doesn't matter as much as people say it does, but it does matter. Because the math behind the central limit theorem assumes you're randomly sampling. Now, thing is, you'll hear people a lot of times say, well, you didn't randomly sample your subjects, participants for your thesis study. I'm really not doing that on purpose to make a point. I was taught they were called subjects, and it's hard to get it out of my head. So you're not randomly sampling your participants for your thesis study. How can you, because they're just people signing up, frankly, it only kind of matters. Okay, it's not that important. People think it is. It's not that important. It's important if you are doing a political poll to represent the population. It's damn important, right? You don't just sample people at an NDP rally. 100%, they're going to dominate this election, right? That's, by the way, that's called, whenever you see somebody who's behind in political polls during an election, what do they say? They're giving a speech saying, well, I see that the polls didn't call anybody in this room. That's the mating cry of the loser. It doesn't matter a whole lot to make the central limit theorem work. It matters for other things, representativeness of the sample. Hell, it matters a lot. But I don't care about that right now. All I care about is, does the central limit theorem work? So to find the probability of x bar, we just use our old friend, the z-score. Hello, z-score, my old friend. Divided by variance again.
Don't ruin that song.
It's the sound of normality. So, things are going to change a little bit here. You can't ruin a song. There's no way I could ruin such a great song. It's possible. It's great. Everything they ever did was great. It really was. They were really something. So this is what we have originally. Remember, it's x minus mean, so subscore minus the mean divided by this variance. All I'm doing now, this isn't magic. X bar is now, we want to find what's different. Minus mu, and what's the variance or the standard deviation of the sampling distribution of the mean? It's sigma over square root n. It's the same damn formula. I've subbed this in for this, and I've subbed this in for this, and I've subbed that for that. You say, well, it's the same damn thing, Dave. Well, yeah, because mu sub x bar equals mu. Okay? They're really, this is not a new formula. I know when you first learned it in 2126, you look at it and go, oh, another formula. No, it's not really another formula. And if you remember the central limit theorem, you will know then what to put in there if you ever use that. Questions so far? How are you guys doing? This feels okay? Feeling strong? Okay. Okay, here's an example. Let's say we have 25 subjects, minus course, and we call them subjects. 25 subjects. And they're given an IQ improvement course. They have their IQs tested after the course. They have a mean IQ of 110. Okay. I don't know. I made this up. There's no such thing as an IQ improvement course. You can't really raise your IQ. It doesn't work that way. You can lower it, just hit yourself in the head with a hammer a bunch of times. But can't really raise it up, okay? But I had to think of something using IQ because I know the variance of IQ of the population. Okay. IQ of the population has a mu mean of 100 and a variant, a sigma squared, or a sigma rather, a standard deviation of 15. Why? Why do I know this? Because IQ tests are designed this way. That's how they work. Most variables we don't know, say, but we actually do for IQ, which is the reason it's used all the time in statistics examples. I imagine in business statistics they use IQ as an example, just because they know the sigma. Okay. So we do this. X bar minus mu over sigma divided by root n, which is 110 minus 100 over 15 divided by 25. Notice how I made this nice and easy so the math would work out. And yeah, I didn't have to use a calculator. The square root of 25 is 5. If you didn't know that, you should know that. 10 over 3 is 3.33. The probability of getting a z-score less than 3.33, I'm sorry, greater than 3.33 is less than 0.00043. Now you might say, I don't think I have that in my Z table in my book. No, you don't. But in my old fancy calculator that my son destroyed, you could put a Z value in and it would come out with a probability. So you look that up on a table. Look, you know how to do these. You know how to do these. What that's saying is it's exceedingly unlikely that this happened by chance. What it's saying is our IQ improvement course works. And if this were true, we could all retire because we could be giving this, we could be selling these late at night on television along with shark cartilage. You haven't seen those infomercials? No? Okay. We'd hire some D-list actor to host the infomercial for us. You know, I don't know, how about Ted McGinley? Some of these jokes are just for me, and I really don't care that you don't get them. So that's fine. We would then conclude that it works. Whatever. There's no problem, though. We don't usually know sigma for a population. We know it for IQ, and if we do know it, that's wonderful. There are other times you can theoretically figure it out. If you're using what's called a binomial expansion, which I'm not going to do. It's such a rare thing to happen that we're not even going to talk about. The expected value of S squared is sigma squared. Remember, unbiased estimator, right? Well, why don't we just throw S squared in there? We can calculate that. That's a piece of cake. Or pi, perhaps, if you prefer pi. Or a delicious burger. Whatever it is, it's pretty easy to do. Just sub in S squared for sigma squared, but now we're going to have two sampling distributions to contend with because we have to worry about the sampling distribution of the variance. So, remember how the sampling distribution of the mean is all the possible, a distribution of all the possible values the mean can take. The sampling distribution of the variance is with this given n, is the distribution of all the possible values the variance can take with a given n. Wow, we have to care about that now too. That's a pain. And remember how do we calculate variance? Right? You remember the variance is simply x minus x bar squared over n minus 1. Now, this is telling us something that the whole thing depends on n. The bigger n is, the smaller the variance is, right? That's the thing. Because it's the bottom of a fraction. If you divide by a bigger number, you get a smaller number. That's one of those properties of the universe. So, we're going to have to take that into account. Take that into account. There it is. So we can't use z. Because z doesn't change depending on the n, does it? It's always the same. You just look it up. Think about a z table. Right? You want 0.05, one-tailed, it's 1.645. It's always 1.645. You want 0.025, one-tailed, or 0.05, two-tailed, or 0.025, one-tailed, it's 1.96. Works that way. Can't do that here. We have to worry about the number of subjects. We have to worry about the number of degrees of freedom. Okay, so we're going to use t, which is x bar minus mu over s. Oh, see, it looks a lot like the old Z formula, doesn't it? The only thing that's different, in fact, is this isn't a sigma anymore, now it's an s, divided by root n. Okay. And again, that's a one-sample t-test. We've all seen it before. So t changes depending upon the number of observations. Once t hits about, by the way, you might notice when you look at a t formula, a t table at the back of a book or something, once t hits about 30, it looks a lot like a z table. It's very similar. The values almost become indistinguishable. So t changes depending upon the number of observations. Degrees of freedom to estimate sigma squared by calculating s squared, to be precise. Right there. In our case, right now, it's going to be n minus 1. Remember, degrees of freedom are not just n minus 1. It's not, this doesn't work that way. They are the number of value. The number of numbers that can be assigned arbitrarily. In our case here, it's going to be n minus 1. That will change depending on the kind of procedure you're using, so keep that in mind. So the answer, if you write on a quiz, when I write degrees of freedom, you can't just write n minus 1. It's not always n minus 1. Sometimes it's like a times b times n minus 1. You know a and b are. It's a pretty powerful technique if you think about it. You have to know anything about the population at all. That's pretty neat. Well, right now I guess we have to know the population mean. Yeah. That's it. You don't have to know the variance, and you don't have to know the shape, because we know the variance, or we can estimate the variance with the sample variance, and the shape, because the central limit there, it's going to be a normal distribution for the sampling distribution. That's pretty cool. Okay, questions so far? All right. What if we had pairs of observations? Well, pairs of observations can be a bit different. Because now if we pair people up, and I know this looks funny on the PDF, there's a reason. If we pair people up, or we have the same person before and after. So let's say we're going to test some blood pressure medication. I don't know. So we measure Craig's blood pressure before, right? And then we give him the medication, we measure it after. We do the same thing with Jay, with Spence, Andy, and everybody else. With pairs of observations. If the blood pressure medication has no effect, what should we get for what should happen between before and after times? There should be no difference. So what we're doing there is we're looking at difference scores. Before minus after minus before. I don't give a crap how we do it. Thing is, what if instead of testing Craig twice, testing Lucas twice, testing Jay twice, whatever. What if we can't do that? Maybe the medication has a long-lasting effect. I don't know. I'm making this up as I go along. These examples are horrible. Why don't we match subjects up on their blood pressure? So we take everybody's blood pressure in class and we match you up. So it turns out that Kelsey and I have exactly the same blood pressure, which seems exceedingly unlikely. So we match the two of us up. You do get the blood pressure medication, I do. We then measure the two of us. We're now considered a pair, right? And we subtract your score from mine. Okay? Still, we expect the scores to be the same, to be 0 if there's no effect. That's why it's x bar sub d. It's the average difference. Standard deviation of the differences divided by the number of pairs. It's the same damn formula. Why don't I have minus mu there? Because mu is 0. Right? So it's, did you like that? Did I just flip away? It's pretty good. So standard deviation, mean of the differences, technically minus the mu sub d, but mu sub d is 0. Standard deviation of the differences divided by the number of pairs. Okay. So not just for individual score, the ultimate pair of observations is the same person tested twice. We can't always do that, so we could use it with matching. Now, one of the things, as far as just as a note on design, you want to be careful about is, usually we randomly assign subjects to groups. If we actually do match people up on whatever variable it is, they're matched up nicely on that variable and not matched up at all on anything else. Just something to keep in mind. Okay. Questions. Do you have questions? Are questions in your head or other parts of your body, which seems unlikely because your brain's in your head? Sure. I know you've seen all this before. Maybe it's that. And all you're going to do is you calculate this and you look it up and see if it's greater than some key value. Go ahead, guys.
So with the mean difference, it might be a silly question. It'd just be like you subtract the two people and then you get all the numbers and then find the mean of all those numbers?
Yeah.
Okay.
That's exactly what it is. See, it's a good clarifying question. Never preface your question with, this may be a stupid question. As a rule, I mean, I'm just saying that when you do that, immediately people think, oh, goodness, and then actually it's a very good question. Other questions? Any actual stupid questions? No? So you guys are good. Making sense, right? It's all stuff you've done before. Except you used to take a day and a half instead of 10 minutes. You sure you have no questions? Okay, that's fine. Fine, have it your way, see if I care. All right. What if your pairs aren't matched? That's a different issue altogether. The pairs aren't matched, right? So maybe you have two populations in that case. In fact, that's what we're trying to find out. That's what you're trying to find out. So, well then the hypotheses are as follows. HO is mu1 equals mu2. The mean of the two groups are the same. Is that H1 is not equal to H2. It could be directional, greater than, could be less than. Let's not worry about that right now. Let's just say not equal to, okay? All right. So those are our two hypotheses. Now, the original T formula, the one I just introduced about 10 minutes ago, is this guy. T equals x bar minus mu over s divided by root n, right? Okay. We had a statistic that we're trying to find out about, right? We had HO in there. And we have some measure of spread. Basically, we call this the error, or in this case, it actually has a term, has a name, it's called the standard error. Standard error of the mean. Okay. So we have a statistic, we got HO, we've got the standard error of the mean. We take a statistic, we subtract something representing a null hypothesis, and we divide by the standard error of the mean. That's for the original T formula. T is actually pretty interesting because it was developed by this guy named Gossett, who published under the name Student, which is kind of cool. He published under that name because his employer didn't want him to be poached away by another company. They liked their scientists publishing, they just didn't want them to get taken, hired away. So when he developed this, he published it under the name Student, which you'll often hear called Student's t-test or a studentized distribution. The guy's name is actually Carl Gossett. Gossett was a quality control guy at Guinness in Dublin, Ireland, which is kind of great. He's doing statistics in a brewery. It's like awesome. It's like my dream job. I don't know why he called it T. I know why F's called F. I don't know why T's called T. Could be maybe let's make something up. I really enjoyed Toblerone. So, what are we going to do? We're going to put the statistics we're interested in, and we're going to subtract the null. So x bar 1 minus x bar 2, subtract mu 1 minus mu 2. You say, wait, what? Practically, actually, that's this. Because our null hypothesis is that mu 1 equals mu 2, which means that mu 1 minus mu 2 is 0. So that goes in. So you're not usually taught the formula on top. You're usually told, oh yeah, it's just x bar 1 minus x bar 2, but technically, really, it's minus mu 1 minus mu 2. Sometimes you'll see in an intro stats book, one of the final hard questions when they make they say, the null hypothesis is the two groups are different by 5 points. Those are never true. Those are never null hypotheses. No one has null hypotheses like that. Just jerk-ass statistics, guys. Right? Doesn't happen. But the nice thing is, this gives us an idea of why it looks like this. So again, it's not a new formula. And divided by the standard error of the mean. Well, it's the standard error of one mean subtracting another mean. So we got to figure that out. But you see why this? Right? Now, the error is a little different. It's the variance of group 1 divided by the number of subjects in group 1 plus the variance of group 2 divided by the number of subjects in group 2. You can subtract distributions. You can't subtract variances. And the variances have to be weighted because, and we talked about this when we talked about coefficient of variation earlier in the course, the bigger the n is, the smaller the variance is. It's just going to work that way. Right? Variance depends on the size of the mean and also the size of n. So the bigger the n is, the smaller the variance is. We have to divide by the number of observations. So we're going to add them together. We're going to add them together, right? And divide by the square root of it because we know we have to get it. The standard error is in the same units. So look, that's where our formula comes from. X bar 1 minus x bar 2, or x bar 2 minus x bar 1, doesn't matter, over the square root of s squared 1 over n sub 1 plus s squared sub 2 over n sub 2. Square root of that whole thing. That's pretty nifty.